All right, let's get started. Couple things. So in terms of housekeeping, so grading. So obviously exam 1's taken care of, homework 1, homework 2, homework 3. Homework 3 has been graded and it's been returned. It's on the cart. So y'all know the drill. Please do me a favor and pick that up off the cart as soon as possible. I also have the solution posted to Blackboard. So if for some reason there's a grading hiccup, just let me know. Okay. How's it going? What's up? What's up?
Hey, it's exactly 11.
Seconds.
Ooh,
Seconds. All right. Homework number 4. Again, it's not due till Wednesday. Although I did have 2 questions sort of before class, and I'll share the results. So first question I got was about problem 2, and it was about in design mode, is it possible that your bolt bearing capacity is just ginormous compared to your bolt shear capacity? And by ginormous, I mean, do you have a bolt shear capacity of 300 kips and a bolt bearing capacity of 600 kips? Is that possible? Yeah, it's possible, especially if you have a lot of bolts. So that's not that unheard of. Those two values start to converge a little bit when you have a fewer number of bolts. So if you have 6 bolts in your connection or 4 bolts in your connection, it's more likely that those two numbers are going to be pretty close together. If you have 18 bolts or 16 bolts or 12 bolts or something like that, it's possible that your bolt bearing connection gets a little farther. But you're not going to know until you just check. Now my second question was in regards to, remind me, it was the problem 1. What was it? It was problem 2. Okay. Okay, so the second question here, I'll go ahead and pull up the homework assignment so everybody sort of sees what we're talking about. Nope. I hit problem. Yeah. So. This one. So it's table 1-52 to lay out the transverse spacing of your bolts. I'll be honest, that really doesn't entirely affect the design. Let me see something. So 836. Okay, so you're going to design the connection using 2 lines of bolts. And so let me see if I can sort of explain what I meant by that. Let me open up the Word document so I can copy the image. Okay, so for that problem, and I'll be honest, I don't remember the number of bolts, so please don't take this as, he said there was 8 bolts. That's not what I'm saying. But let's just say for the sake of discussion that you end up using 8 bolts. Okay, first off, the problem stated that you are to design this connection using 2 lines of bolts. Now let's go back to terminology. Who remembers which way a line of bolts runs? Parallel to what? The stress, right? We're yanking on this thing left and right. So our lines of bolts are going left and right. So what this problem is stating is that we're going to use 2 lines of bolts. So one's going to be something about like that, and one's going to be something about like that. So if we were using 8 bolts, it would be 1, 2, 3, 4, 1, 2, 3, 4. Now, as for how far apart those bolts should be spaced or from the edge, you got to figure that out. But what you might not know, and the reason for that note is, well, you have 2 lines of bolts, but what's this distance and what's that distance? Like, what's that and what's that? And that's what that table was for, table 1-7A on page 1-52. So if you go to that table, it's right before the WT section, so it's right at the end of table 1-7. You'll have workable gauges and angle legs. So on the top row, it says leg, and it says 12, 10, 8, 7. So those are the leg sizes. So this problem, what was it? Was it an L4, 6x6? What was it? 8. 8 by 8. Okay? And so if you have 8 by 8, and we have 2 rows. You look over here on the image, and so we're going to use G1 and G2. And so for an 8-leg angle, what are G1 and G2? Does everybody see that? They're 3, right? So this is page 1-52. They're 3. So this distance is going to be 3 inches, and that distance is going to be 3 inches. Those are just workable gauges for the purpose of fabrication. And so I put that note in there so that everybody would have that dimension. Now, I'm obviously not giving you these dimensions this way, like that distance or these, because you can determine those through the course of designing your bolted connection. But those 2 you didn't have right offhand, so I just said, well, I'm just going to go ahead and give them to you. Did that make sense? And so is everybody else okay with that? So that was why you got that. Do you have a question? Oh, I thought you had. Everybody, any others? Don't worry, I'm going to give you time on Monday as well because the homework's due on Wednesday, so I'll make sure and open up for questions on Monday right before you submit. Sound good? Okay. Now, I was sort of mentioning this, earlier part of class, but I really wasn't kidding. We're going to start talking about welds, and in all honesty, I think you're going to find there's some terminology and some things that you need to be aware of, but really this topic, of all the topics that we cover in this class, this one's the easiest. It really is. So let's talk about welds. I'm just curious about something. How many of you have ever welded anything? I know a few of you have, at least here recently with the steel bridge, you went to that DOH training workshop on welding. Who would say that welding is easier than bolting something together? Nobody, right? Welding, I don't even like to say it's a skill. Welding's an art form, man. It takes work. It really does. See, me, if I have a slightly mediocre weld, I'm having a really good day because it's not good. I can take piece of steel A and piece of steel B and hit the electrode on it until they're melted together. And out of maybe 10 welds that I deposit, maybe one or 2 of them look good, but I'm not good. I'll be the first person to admit. Just keep grinding it until you get it right. It's funny you mentioned that because I'm gonna bring up something about that here in a second. But yeah, welding is a skill. I mean, I'll say this, like if you get a job, like if you spend, the required time and put in the required practice and get the certifications necessary to do something like be a welder on a nuclear submarine or something like that, you're going to make some cash, let me tell you. I mean, it is because welding is such a difficult, skill to pick up right off the bat. It takes some time to learn. It takes some effort. Welders do pretty well. They can make some serious change. So it's a very, very decent career. I want to talk a little bit about welding to give you all kind of an idea of how welding comes about, the different types of processes that we use in engineering, the different types of welding joints that we have, how we determine capacities, and so on and so forth. I think I would be remiss if I didn't at least mention D1.1. We're not going to use D1.1 directly, but a lot of the codes and provisions that we're using come from the American Welding Society's D1.1 structural welding code for steel, and it's one of the most consulted codes really in the world. And so most of what we do when it comes to structural design kind of comes from this. I mean, we take a lot of the mechanics and the material specs from AWS, and then we put our LRFD spin on it. But in the end, a lot of this theory and whatnot and procedures comes from documents like this. But first thing I want to do is I want to talk about welding procedures. Now, let me be clear. I'm talking about welding procedures that are used in structural applications. So one thing you won't hear me talking about, for instance, is like TIG welding or something like that, because we're not talking about welding, in automotive applications or some other mechanical system. We're talking about the types of welds that we deposit for buildings and for bridges and transmission poles and things like that. We're talking about large-scale systems and the type of welding that we do there. Now, some of these terms you probably have never heard before. You probably never heard of the term shielded metal arc welding or gas metal arc welding or flux core arc welding or something like that. However, when you look at the method and go, oh, that's MIG welding or something like that, you'll kind of see what I'm talking about. So, but these are sort of the scientific terms for the 4 fundamental methods that we use in structural engineering. And so the first is shielded metal arc welding. And you probably have never used the term shielded metal arc welding, but if you've ever been around welding or done any type of welding, you have probably heard of stick welding, right? Everybody's probably heard of stick welding, and stick welding is probably one of the 2 most common types of weld applications done in large-scale structural systems, the other being MIG welding. Okay? Although I would argue that if we're doing large-scale welds, stick welding is still predominantly the most common. And so the idea is that you have one end of your lead attached to the member, the other end attached to a combustible or a consumable electrode. And so once that electrode comes into contact with your joint, the electric circuit is completed, electricity begins to flow, and that electrode begins to melt. So right there at the end, or at the point where the circuit is complete, you've got a lot of amperage flowing through that particular point, so much so that you essentially create 3 molten pools of metal. You're melting the electrode as well as the 2 components that you're welding together. So you got a big molten pool of metal. And so once that cools, those 3 molten pools sort of solidify into one joint, and there you've created your connection. So just so everybody's 100% clear, welding is not the same thing as gluing. You're not depositing some metal and gluing piece of steel A to piece of steel B. You're actually melting everything and creating a cohesive joint. And so one of the things that you have to do when you become a certified welder is there's a number of things that make a good and solid welded connection. One of those components is what's called weld penetration. So that not only do you want to have a solidly welded joint, but you want that melted region to penetrate well enough into the base metal such that you're generating a solid connection. And there's a couple other things like hydrogen embrittlement and things like that, which I'll talking about here in a sec. Speaking of hydrogen embrittlement, when you see a stick weld, if you see somebody with a stick weld, here's the electrode. If you've ever seen an electrode, it's basically, I wish I had some with me, I should have brought some, but essentially it's a solid metal wire, and it's sort of coated by this white sort of granular sand looking stuff, and it's got this sort of flux coating. And so what happens is when you complete that circuit, not only do you melt the weld metal and the base metal, but you activate that flux coating. And so what happens is it generates this gaseous shield that surrounds where the welded connection is being formed. And what that gas shield does is it basically tries to prevent impurities from getting into that molten pool of metal. The biggest one that we're really worried about is hydrogen in the ambient atmosphere. If hydrogen gets into welds, that's really, really bad because that generates a brittle weld, and brittle welds are no good because brittle welds mean cracked welds, and cracked welds are really no good. And so that's generally the process known as shielded metal arc welding or stick welding. The other one that's probably the most familiar with everybody, and if any of you, have done this back home or your parents have this in the garage or something, if you do any welding, let's say at home, you probably have something like a MIG welder, okay? So gas metal arc welding or MIG welding is arguably the second most common type of welding that we perform in structural engineering. And so the difference between stick welding and MIG welding from a procedure standpoint is here's the welder with the electrode. Once that electrode is consumed, the welding has to stop. You get another electrode and start over. With MIG welding, you have a continuous spool of electrode that basically, you have your gun, you hit a trigger, and that electrode just continuously spits out. So you can sit there and weld all day long as you have enough electrode. There's no stop, start, stop, start, stop, start procedure. So the thing with MIG welding is it's very, very fast, and so because of that, it's usually a little more economical. The problem is MIG welding sort of does have a little bit of a cap in terms of the size of the weld that you can deposit and how much weld penetration that you get. So if you really need a really deep, strong weld, stick welding does still seem to be the way to go, unless you're using some type of robotic approach, and I'll mention some of those here in a second. Now, when you standard MIG welding operations, you have not only your continuous feed of electrode that's coming through the end of the gun, but you'll also have a gas shield. You'll have a big tank of gas, and so usually when you're carting around a MIG welder, let's say around the shop, you're going to have not only the base unit that's generating your voltage and current for the welding, but there's also usually a big tank attached to it that you'll wheel around, because that tank provides the gas shield that sort of neutralizes, again, the hydrogen and any other impurities in the atmosphere. So this is also one thing I'll mention. This is one process that can be automated. And so if you're trying to do welding with some sort of device or some sort of robot, which is becoming more and more common, you tend to see stuff like this used a little bit more often because it's a little bit easier to automate. Now, if you've got a small little Lincoln Electric MIG welder, in your garage, it's possible that you don't have a big tank, a big gas shield that you use, because instead you'll use what's called a flux cord electrode. And so flux cord arc welding is similar to MIG welding, or similar to the gas metal arc welding process, except the wire itself has a similar coating. You can always tell when a weld has been deposited using a flux cord process. I'm going to skip ahead a little bit. Whenever you see a flux core weld, you deposit it, and there's this sort of white, milky coating around the weld that you sort of have to chip off. That's the coating that's meant to prevent those impurities from getting into the weld. I'd say the fourth most common, that's becoming a little bit more common nowadays in structural applications, is submerged arc welding, or SAW welding. And this is really only performed by automatic or sort of like a machine type method. And so really a submerged arc weld is really going to be most valuable when you have a long continuous weld, maybe trying to weld, I don't know, a top flange to a web or something like that, where you have a single weld going along a long member. Submerged welding is going to work very well. The reason why is because the QA/QC is very high. What ends up happening is that there's actually two sort of nozzles for a submerged arc weld. There's one in front which is depositing this sort of like granular flux. It's almost like kitty litter, but it's a little bit finer. And the welding actually occurs under this deposited flux. So you can see as the submerged arc weld is going along the girder, you can see here's that sort of kitty litter, and the weld is actually occurring under this. So you get a lot of quality assurance and quality control with this type of weld. But again, it's only really appropriate if you have a really long continuous weld. So is everybody okay with welding procedures? Anybody have any questions on that? Yes?
You didn't mention friction welding. What was that for?
So you're friction welding. So you're talking about if you have like shaft A and shaft B, and you're and you do that. So that's I mean, it is a type of welding, but we're really not doing that very much in buildings. Like when you're trying to weld like a gusset plate to a truss. We're not. The geometry doesn't work. I mean, it is a type of weld that we can obviously employ, but it's really more appropriate for something like a mechanical application, like a rotating shaft, a car, something like that. We really wouldn't use it in buildings. There's also the Mythbusters approach where they take the two plates and then they stick the dynamite on top. And I'm kidding, but in all seriousness, it wouldn't really work just for our geometry. So, but yeah, no, it's a valid welding procedure. So, okay, now regardless of what welding procedure you utilize, you're gonna, whether it's a stick weld, MIG weld, what have you, there are a few different types of welds that you're going to deposit. And if you ever have welded anything, what's the first weld that you deposit? It's a tack weld, okay? And so what a tack weld is for is it's just a temporary weld that's used to hold the part in place before you place a more extensive weld. So the idea is, let's say this is a beam and this is a clip angle where I've got bolt holes going through here, and so you'll have, let's say, a column here. And so when you transport this beam to site, there's a little clip angle welded to it, and so you'll bolt this beam to the column like so. And so that means you have to weld this angle to the beam. And so the first thing that you'll do is you'll line that angle up right where you want it to be, get all your measurements done. It's like the whole measure twice, cut once, so it's measure twice, weld once. So the first weld that you'll do is just a couple quick hits of the weld just to place a small little weld to hold it in place. Like, honestly, those tack welds are a little big, but in the end, you just want that part to sit still. And then what you'll do is you'll go in, measure it again, make sure everything's good and in place where it needs to be before you deposit your final weld. So the idea is if it's in the wrong place, you can grind it off and start over, but you don't want to have to grind it off if the whole thing's been welded. That's just a big deal. So it's really more of a fabrication concern than a design one. All in all, the most common weld that is placed in structural engineering, period, is the fillet weld, okay? And this is the one that we as structural engineers really need to worry about designing. I have here roughly 85% of all welded joints are fillet welds, but I'd almost go as far to say it's probably even more like 90 in building and bridge applications. So you have piece of metal A lapped on top of piece of metal B, and you run a bead of weld along that joint, fusing those parts together. And so fillet welds can be continuous. It can be a continuous weld along your connection. It could also be done as a series of shorter welds, like here's a weld, here's a weld, here's a weld, here's a weld. And so we call those stitch welds. So if you've ever seen that, that's what that means. But arguably the most common type of weld is the fillet weld. The second most common type of weld is what's called a groove weld. You'll probably never hear groove welds referred to as groove welds in practice because there's two different types of groove welds that are really what people refer to, and that's either a complete joint penetration weld or a partial joint penetration weld, and that's or CJP or PJP. And there's really not, I'll say this, there's really not a whole lot of design that's associated with groove welds because what we do is we spec out that weld such that the capacity is governed by the strength of the base metal, not the strength of the weld metal. In other words, we want the base metal to be the weaker component. So as long as the weld is stronger than that, we're good. That's not really the biggest concern. It is with weld metal, with fillet welds, but not with CJP or PJP. What's a little less common is something like a plug weld or a slot weld. So that can be used to maybe like transmit shear when you have a plate or a plate lapped onto another plate. And so the idea is, you might have a plate lapped onto another plate. One plate has holes drilled into it, the other doesn't. So you lap them onto one another and you just fill that with weld metal until you join them together. It can prevent buckling of lap parts and things like that, but in all honesty, it's pretty rare. No, yes. No, they're kind of their own thing. They're because you're really sort of just melting the tip of that and just shoving it in, so it's kind of its own thing. In fact, it's so much its own thing that the spec handles it in its own section. It's not even handled in Chapter I or Chapter J. It's handled in Chapter I. So that's a good question. Anything else? Now these are the types of welds. We also have to consider and when I'm talking about terminology, I want to make sure that everybody's clear on terminology. For instance, if I have a fillet weld could be placed on a lap joint. It could also be placed on a T-joint. It could be placed on a corner joint. So the joints that I'm talking about are just the ways in which, plate A and plate B would be, put together. So a butt joint would be if plate A and plate A butted up against one another, a T-joint or a lap joint, T. So like a flange to a web connection would be very much like a T-joint. A lap joint is just a lap two on top of one another. So, for instance, that's a lap joint where you have plate A and plate B and they're just lapped on top of one another. And then corner joints and edge joints. Another important factor to consider is the weld position. Anybody who's ever done any welding will tell you that welding in a flat or horizontal position is obviously the easiest. That if you have to weld overhead or if you have to weld in a vertical position, it makes the welding process much more difficult because you have to ensure that, hot molten weld metal doesn't drip on you. And so it's pretty difficult. And so when you start getting into vertical welding or overhead welding, really the skill of the welder, that's where the skill of the welder really comes into play. And so if you're in the shop and you're fabricating pieces of steel for a project, you want to try and use flat or horizontal positions as much as you can. But sometimes that's impossible, but we're really trying to avoid vertical or overhead whenever we can. Now, has anybody ever seen like drawings that show like welding, like weld details? They can be nuts, can't they? There's arrows and symbols and crap all over the place. And it can be really complicated, especially when you get into mechanical engineering projects or something like that. We're obviously not going to worry about that in here, but there are a couple things I sort of want to show you so that you're aware. So first off, really the two weld symbols that I want you to be aware of are this and this. So let me sort of explain what's going on here and here. So if I have a symbol, if I have a weld that's like this, so it's a 1/4 inch and it has this triangle and there's a 6. Okay? So the 1/4 inch indicates basically the size of that weld. Okay? And so the welder, depending upon the electrode and the speed and the amperage and whatnot, the welder can specify the size of that weld pretty easily. So 1/4 inch, that's what that is. The triangle indicates that it is in fact a fillet weld. And you can see here on the previous slide that if you were having a plug weld or something like that, that the symbol would change. So fillet welds are obviously going to be the most common. If you have a single triangle on the arrow side, that means the weld goes here. If you had 2 triangles, like on either side, that means that the weld not only goes here, but it goes there. So if all I had was the upper triangle, that would mean it would go right there. But that's very uncommon. You just put the arrow where the weld's going to be. And then the 6 indicates how long the weld is. So this would be a 1/4 inch fillet weld that's 6 inches long that's placed on the side of where the arrow is. The only other point that I would mention is that if you're doing this and there's, let me see if my pen's going to work. If you're doing this and you had, it's not going to work. If you had a little flag sticking up like right here or a little flag sticking up right here that looks like this or like this, that would indicate that that is a weld that is to be done in the field as opposed to a weld that's done in the shop. So I'm not wanting you to memorize everything. I just want you to, this is really all I want you to be able to draw. So when we do calcs and do problems in here, the welds are going to be specified like this. So everybody okay with that? Okay. Let's talk about the math. Let's talk about the capacity. Now, in this course, I'm only going to focus on fillet welds just because they are the most common, okay? And what you're going to find is that the capacity of a fillet weld is really, really easy to compute if you understand some basic mechanics. Now, the first thing that you need to understand in terms of mechanics is this term called the throat, or the effective throat of a weld. And so the effective throat of a weld is basically what defines how strong the weld is. So what we do when we compute capacity is we assume two things. Number one, we assume that the capacity is defined by the area of the effective throat. And so what is the effective throat? The effective throat is the distance from the root of the weld to the face of the weld. And so if you have a weld that's deposited something like this, and we assume that's a 45-45 triangle, we can do some pretty easy trig to figure out how far it is from the root of the weld, where those two plates meet, to the face of the weld. The face of the weld being what you see when you look at it. The second thing is that regardless of the weld orientation, we always assume that the welds are going to resist loads that are going to be transferred through a shear force. And so whenever you hear the word shear in structural steel design, a certain number should pop up in your head. What number is that? Say it again. 0.6, right? Because remember, the von Mises yield criterion states that in shear, the nominal, or the capacity is about 60% of the nominal stress. Is everybody okay with that? All right. So let's take the throat first. So the distance from the root of the weld to the face of the weld, well, sorry. Oh, I got a couple other things I want to mention. I'm sorry. I'm getting ahead of myself. All right. I want to talk a little bit about weld orientation first. So let's make sure that we're clear on some terminology. So what I have here is I have a plate lapped on top of another plate. And so I have three different images I want to show you. So this over here on the left, this is a longitudinal weld. This over here in the middle, this is a transverse weld. And this is inclined. And I'm just showing you the incline just to give you kind of an idea of the behavior. So we have a longitudinal weld, a transverse weld, and an inclined weld. Okay? Now, this graph shows you how strong welds are as a function of their orientation. Okay? So this long curve over here, this is representative of a longitudinal weld. This is the ones here on the side. This one here up top, this one up here, that is a transverse weld. And everything in between, those are inclined. Okay? Now the way that welds behave, what happens is this. As that angle increases, what happens is the weld gets stronger, but it also gets more brittle, okay? Or it gets less ductile, I guess would be a better way of putting it. In other words, if you use a transverse weld can resist more load than a longitudinal weld. But what happens is it doesn't deform much. So you load, and boom, it goes. Whereas a longitudinal weld, it's a little weaker, but it's going to show a lot more deformation before it fails. So a couple things to keep in mind. What we're going to do and what the code allows you to do in design is we're basically going to assume that longitudinal welds and transverse welds have the same capacity. Because the code allows you to do that, and that's a pretty safe, conservative assumption. But I do want everybody to be on the same page, okay? If you are ever designing a connection, like you get out of here and you've been practicing for 10 years, you call me and you say, hey, I have a question about this welded connection, and you show me the drawings, and it looks something like this, what I'm going to do is I'm going to say, hey, I need you to come to my office. You're going to come to my office. I'm going to ask you to stick your hand out, and I'm going to do that, okay? Don't ever design a welded connection with only transverse welds. There's no problem with combining longitudinal and transverse. That's fine. There's no issue with that. But if you have a connection with only transverse welds, that connection is very, very brittle. Once it fails, it's going to fail quick. And you can just see that here. So we never use transverse welds alone. You can use a transverse weld with a longitudinal weld, but yeah. So hold on. Give me one sec. I'm going to pause this real quick. So long story short, don't use just a transverse weld because McDonald's and ice cream and all that. Okay. All right. So let's get back to capacity, okay? And we'll cover this, and then we'll probably sort of call it. So, like I said, the capacity of a fillet weld is determined by this dimension, the effective throat, which is defined as from the distance from the root of the weld to the face of the weld. And so if you look right here, okay, if I trace this, this, and this, that's a 45, 45, 90 triangle. And so if I know how the weld size by that distance A, and so we use the letter A to define how big a weld is. So if I know A, I can determine that distance by just using a little bit of trig, right? What's the sine of 45 degrees or the cosine of 45 degrees? It's 1 over the square root of 2. And so typically when we compute that capacity, we just use the term 0.707. And so if you see this 0.707, it's just the weld leg size times that, which will tell us that distance from here to here. So everybody okay with that? Okay, so that's the effective throat. And so what we do is we take the effective throat times the length of the weld, and that sort of gives us the quote-unquote area. Now, the way that we compute the capacity is this. So this is a lot like bolts. So with bolts, remember when we had a bolt going through a plate, we had to check really whether or not two things were going to fail, the bolt or the plate. And so the plate was going to fail through like a bolt hole ovalization, a bolt tear out, something like that. Well, with welds, we have two similar investigations we need to perform. Is the weld metal going to fail or the base metal going to fail? And so we take each one of those independently. Now, the equations are defined out of section J2.3 or section J2, but really, it's going to sound weird, but the equations don't really matter a whole lot, because what this area is and what this nominal stress is and what this area is and what this nominal stress is depends on what you're looking at, okay? And so what I want everybody to do is this. I want everybody to turn to table J2.5, okay? Now, this is in the back. This is in the spec. We're in chapter J. So you should already have like one tab around chapter J, because that's where the bolt provisions are. So chapter J3 or section J3 is on the bolts. J2 is on the welds. So I know everybody brought with them their AISC 15th edition steel construction manual. All right. And so I want everybody to turn to section J2. And if you're turning through J2, you should see a few different tables right out the bat. You should see, effective throat J2.1, effective throat of flare groove welds, PJP welds, so on and so forth. But what I want you to do is turn to page 123, so 16.1-123. And you should see a big old table that says available strength of welded joints. So is everybody there? Everybody's there that brought their AISC 15th edition steel construction manual with them, right? I'm looking. I see a few. I see a few. All right. So 16.1-123. And so right off the bat, I want you to look at some of these entries. So the first row, remember how I said that groove welds, or for instance CJP groove welds, how the tension or the capacity is really controlled by the base metal, so there's really not a whole lot of design when it comes to the weld. That's kind of what's going on here. So we have CJP welds, we have PJP welds, but if you turn the page, we have fillet welds. So if you turn to 16.1-124, we've got fillet welds. Now, we're loading our welds in shear. And so if you look where it says the next, or the one below where it says tension or compression in point joint parallel to a weld is permitted to be neglected. That's sort of what I was saying earlier, where we just assume everything's in shear. But let's take a look at the shear capacity. So see how the shear capacity is split up into base metal and weld metal? Does everybody see that? On the following page, this is 124. In fact, what you should be looking at is something like this. So does everybody see this? Everybody with me? I know you. Don't forget your AISC 15th edition steel construction. I see that too. One of you should just say, no, this is mine. Oh my goodness. All right. So first off, there's a couple things that show up, okay? Let's talk about the phi value. The phi value is 0.75. If you're wondering what omega is, phi is for LRFD, omega is for ASD, for allowable strength design. So we're ignoring that. We don't need to worry about it. What about the nominal stress? What's going on with the nominal stress? What number do you see pop up? 0.6. Remember, we're talking about a capacity in shear, okay? What do we see for the effective area? Well, it says refer to section J2.2a. If you read section J2.2a, it says the effective area of a weld shall be the length multiplied by the effective throw. Now, what's going on with this FEXX? FEXX is the filler metal classification. So, for instance, if you go to Airgas and you buy an E70 electrode, that electrode has a nominal strength of 70 KSI. You buy an E60 electrode, that's going to be 60 KSI. So that's just dependent upon what electrodes you buy at, you know, Lowe's or wherever. So the effective area of the weld is the effective throat, 0.707 times the length. We know the nominal weld capacity and we know phi. So phi RN for a weld is pretty easy to compute. All you need is the classification of the metal. You need the length of the weld, and you need the size of the weld. And that's it. It's a pretty plug-and-chug expression. All right? Everybody okay with that? Now when we get to the base metal says, well, that's governed by section J4. Okay? What I'm going to do is this. We're running short on time. We'll sort of cover that next time. However, if you open section J4, you're going to find that this is a pretty straightforward process, and like I said, this is pretty easy. I'm running out of time, so we're just going to call it. I will see you all next week. Y'all have a wonderful weekend.